want to say something about the wave equation. It's a topic which is covered in our linear algebra courses and very, very classical. So it started in the end of the 17th century, beginning 18th century. And it can also be done in the discrete on finite networks, graphs, or simplicial complexes. I'm just chose the language of these simplicial complexes, and so things are then very, very similar to the classical case, because if you have an exterior derivative, we can look at partial differential equations like heat equation, the wave equation, the Laplace equation, Eikenal equation. Whatever is done in the continuum you can also do in the discrete. We worked on this maybe 7 years ago. Annie Ruck was writing a thesis on this, and it was originally a HCRP project here, where we worked on some partial differential equations on graphs. It's a lot of fun and fancy, because it is not so classical. I mean, this is a few hundred years old. On networks, one only started to be interested more recently. But the setup is very, very, very similar. It's just we have a, say, a wave equation, and the L is now just a matrix, a finite matrix. And so it is something which we can deal with in linear algebra. And so it's actually, technically, it's then an ordinary differential equation, because there is only time. But think of this as a discrete version of a partial differential operator. And so we have like the Laplacian, and so we have, but the framework is explicit solutions which we have. This is something we can write down. We have learned how to write down in general, say for the wave equation, where the vk are the sine functions. We have used the sine function as our basis. Here, this the same thing works. So you write your initial condition and your initial velocity in terms of the eigenvectors, and then you can write down the explicit solution, and you can just differentiate. If you differentiate this with respect to t twice, you get the lambda k. If you differentiate this with respect to t, so you get the cosine, and then the square root of lambda k goes out, so at t equal to 0, this matches the initial velocity. It's exactly what we do in the wave equation using Fourier theory. So there is also an analog of the matrix method. We have seen the matrix exponential, and so you can use kind of the operator method. What is nice, if the operator L is a square, like in the one-dimensional case, right? In the one-dimensional case, the Laplacian, the second derivative, is a square of the first derivative, I times the first derivative. And so that's actually the Dirac operator in one dimension. It's the simplest Dirac operator. And then you can write down the solution classically as the matrix exponential of the derivative. And the matrix exponential of the derivative is nothing else than the Taylor series. And it's no accident that Brooke Taylor was one of the first who looked at the wave equation, because that's just what it is. It's a translation. You have a wave translating to the left and a wave translating to the right. That's what you have. So if you look at the wave, if you make a disturbance here, there is a wave going to the left and a wave going to the right. And it's a, yeah, it looks like a complicated motion, but it's made of very simple motion, oscillation. It's a combination of different oscillations. And this happens also in the discrete. Now in the discrete, it's kind of more interesting, even because the lambda k are not just minus k square like in the Fourier case. So it's kind of more interesting, because the frequencies are not compatible. It's not rationally dependent. So it's kind of can become more interesting, but in principle it's exactly the same framework. I like also to think about it using the D'Alembert method. D'Alembert was also Jean Leurent. D'Alembert was also one of the first who thought about the wave equation, and he saw it as a combination of a wave going to the left. This is a solution of the transport equation, and a solution of another transport equation, one to the left, one to the right. So in some sense, what D'Alembert did, he made it relativistically invariant. That's what then Dirac did, you know, the Schrödinger equation. If you look at the Schrödinger equation here, the Schrödinger equation, one of these equations is the Schrödinger equation for D. That's not, if you take here, replace ID with L, this is not relativistically invariant, but if you take two, so you look also at antiparticles and antiparticles and antiparticles, you get the relativistic, you get to the wave equation. This is nothing else than the wave equation. That's why quantum mechanics is also called wave mechanics. It's essentially the same. It's just that the wave equation has kind of two parts. There is a particle and an antiparticle solution. So that was Dirac's idea. So everything is really just nice linear algebra, and maybe I just show a couple of, you know, pictures. You can do that. You can, you know, put that in the computer and see what happens. For example, you can take a circular network and see what happens. You take a disturbance at one point and you see what happens. Maybe I show a picture of that, how the wave, you see more details in the kind of, if you slow it down and you see the propagation, it's actually kind of very interesting that also there's this Huygens principle that every part of the wave kind of radiates also again in both direction or in all direction. Huygens was also one of the important guys in that field, and so you see that quite nicely. I also was interested in kind of, you know, higher dimensions. You take it on I had an example on a kind of like a carpet. I just took just one of the simplest kind of two-dimensional domains you can think of. Maybe I show a picture of that, and I also put it on a sphere. You have a sphere and you look what happens. You take your disturbance at one point and you let it flow. So these wave equations which I look, these are actually on all K forms. So you look at it on, so if you take a graph, for example, and you look at the simplicial complex associated to it, so there are functions on vertices, so the scalar part, the functions on edges, which are one forms, functions, which is kind of the electromagnetism, then functions on triangles, etc. So you can, and each of these parts are invariant under the wave flow because the L is just direct sum, the partition matrix. You can look at each sector individually. Also, kind of just a little remark, which is kind of strange. If you look at the classical wave equation, what happens is if you start a wave at some point and you are in distance away, so there is a finite propagation speed. So at that point, I don't know that this wave has started. When you see a supernova explode, that has happened a long, long time ago. We don't know that it happened before the wave has actually reached us. Now in the discrete, and that's kind of maybe philosophically interesting, when you take a discrete space or discretized space, this is no more true that you have a finite propagation speed. So it looks like this if you look at the experiments, but what you can see this, I mean, if you look at these solutions, these explicit solutions, these analytic functions in T, and polynomials, even trig polynomials in T, you can write them down. And what happens is, even when you are far away and you start here a disturbance, immediately you actually already see some change here. So that's kind of, you know, indication that this is not the right framework. And how you can change that is you just discretize also time. If you also discretize time, you make here a discrete time. And I wrote once a paper about that just for numerical purposes. It's actually good to have a discrete map. Maybe I just should mention maybe this article, maybe I display this article kind of Annie. We just signed some notes from that research. And also in this context, what is interesting, you can also look at variants of the wave equation where you replace the d star with the inner derivative ix, which is also a map from k+1 forms to k forms. And so this is the Cartan magic formula for the Lie derivative. So there is a kind of directional wave equation which you can study also. I'm also interested in the question what happens in that framework when you have open subsets of a network, and what happens then when you kind of when you split the dynamics. You have the open set and the closed set, and when you split it, then of course the wave equations stay and the eigenvalues have become smaller. So if I take a simplicial complex, take one zero-dimensional point away, then I have an open set, and I can also at the dynamics of this open set. So it's quite a nice playground. That's it for today.